Yes, hello and welcome again to CPAIOR 2020. So this is the second day of CPAIOR conference, and we had yesterday a very nice master class with great talks and a lot of discussions and very active participants. We hope that also today in all sessions you will be very active, and feel free please to post questions in the chat and then we will ask the speakers. So all the videos from yesterday you can find in YouTube channel of CPAIOR, and some of them will be just uploaded soon. So today we start with our first invited speaker and with other sessions. And it's my great pleasure to introduce to you Professor Georg Gottlob, who was professor at the TU Vienna for almost 20 years. And in 2006, he moved to Oxford, where he is now a Royal Society Research Professor at the Computer Science Department of the University of Oxford. Georg is well known for his work in different areas, so he's leading researcher in several areas. That is maybe what it makes him unique. So he had great results in AI, especially in logic and knowledge representation, database theory and query processing, web data extraction, and also in constraint satisfaction in hypergraph decomposition techniques. So he shared HCAI 2003 and ACM POTS 2000. Except theoretical results, Georg is also interested on application of results in practice. And he's a co-founder of 3 companies until now, so the Leakstore, Rapidity, and Deep Reason. And for his work in different areas in research, he received several awards. And I will just name some of them because there are a lot of them, but Wittgenstein Prize is one of those, Ada Lovelace Medal, ESC Grant, Advanced Grant. He's also ACM Fellow, ACAI Fellow, Fellow of the Royal Society, then a member of Austrian and German Academy of Sciences and so on. And I know that just last week on Friday, he got the 3rd or 4th honorary doctorate from University of Vienna. So I'm not going to list all his contributions, and I think you will like to hear his talk. So it's a pleasure to have you here, Georg. Thank you very much, and the floor is yours.
Thank you very much, Nysret, for the introduction. So you mentioned that I worked on AI and also on databases, and in fact, this talk will be a little bit at the edge, at the cutting edge of these 2 disciplines. And well, it will be presented in forms of queries and answers, but it will be generally a talk. I will just have some slides that ask questions, and then I will try to answer these questions. And then, of course, afterwards, you can have more questions. Okay. So this is also, I want to point out that this work is currently the current version, part of this work is carried out within a project called Hypertree, which is funded by the Austrian National Science Foundation FWF. And this is about hypergraphs, and here you see a beautiful picture which actually shows a Venn diagram, but I think it's a beautiful, nice picture, especially for the colors. I mean, these colors were very famous in the 60s, or these pastel colors, and now they are, I think they have a comeback right now, which maybe says something about our times. So what is this all about? What is this talk all about? So that's my first question, actually. So Hypertree decompositions and similar decompositions, because I will speak about several types of decompositions in this talk, are hypergraph-based methods for automatically decomposing constraint satisfaction problems, or CSPs, and conjunctive queries, and for generating efficient solutions or solution plans. Okay, so basically we have a CSP or a conjunctive database query, and I will very briefly show you some examples here. And the CSP or the query is associated with to each query we can associate a hypertree with, or to each CSP we can associate a hypertree with. And if this width is low, then we have good algorithms for solving it. And in general, this width generalizes acyclicity in a certain sense. But as you may gather, hypergraph acyclicity, and as I will show, hypergraph acyclicity is a little bit more complex, a more complex notion than just graph acyclicity. Okay, so actually we have not only two problems that we will consider to be equivalent here: CSP, constraint satisfaction problems, Boolean conjunctive queries. Here I will just look at Boolean queries for simplicity, but we could of course also look at queries with a result, but for simplicity. Yeah, so we have a yes and no answer. Queries with yes, no answer. These are Boolean conjunctive queries. I will show you examples. And the homomorphism problem. These are three different problems that occur in different disciplines, in different applications, but actually it's the same problem. In practical, I will also come back to this. Is it really the same problem? Formally, it's the same problem. Practically, there may be differences that I will highlight maybe near the end of the talk. So, as I said, these are important problems in different areas, but what is, and it's the same problem as you will see, but what is actually the main interesting aspect of this problem is that they are hypergraph-based. They are not really the best way of describing the structure of these problems is via hypergraphs and not via graphs. So here you have an example of a constraint satisfaction problem. Now, this is a very concrete example. I call it combinatorial crossword puzzle. It's a crossword puzzle where you don't have to know anything. You don't have, if they ask you, they don't ask you river in Russia or things like that. They just give you words, and this is the horizontal words for one horizontal, so that would be for these fields here. And you can imagine that all these are variables, and you can fill these variables with letters such that they match one of these words. Okay, so each of these fields could be considered a variable. The possible values are the values of the alphabet, but what you want is, you want of course to fill this so that one of these words, for instance, panda, can be placed here. Okay, and then you have also vertical rows. Okay, and then you want to fill them with those words. So for instance, for one vertical, if you write panda here, then you could write Petra here, but of course this variable can only will then be replaced with a P. Okay, panda, Petra, panda, and Petra. Okay, now as you can see here, and I don't have to explain very much, the structure of this is much more a hypergraph than a graph. So you see, each word here corresponds to an edge, but an edge with multiple vertices, and the vertices are connected at some point through other hyper edges, basically. Yeah. So this is the very structure of this problem, and of course, without any further explanation, you will see that this corresponds more to a hypergraph than to a graph. Okay. In this case, actually, it's also a planar hypergraph, but I will not comment on this. So now let's look at an equivalent problem of this. An equivalent problem is answering a conjunctive database query. In this case, let's say a Boolean query, okay? So you have a database, this is a university database, and you have students which are enrolled in some courses, and that's some date. I don't know, it's not even, this is an old example that I used to teach in my own courses actually, which I taught in 2003 before moving to Oxford. So that's why you see these numbers here, but the example has changed. In a few years, this could be the birth dates of students actually, but let's say it's the enrollment dates of professors here, okay? Then this is a teaching relation. McLean teaches algebra, what else? And he has the March slot or whatever, okay? And then you have another very interesting relation here, which is a parent relation. If you have people who are parents of other people, especially teachers who are parents of students, then you have this parent relation here. And why do you want to have that? Because you want to answer queries like, is there a teacher having a child enrolled in his or her own course? Okay, in her own course or his own course. Okay, why is that interesting? Because, for instance, it's forbidden. Yeah, and the university wants to check this compliance with this rule. Yeah. Okay, or at least there have to be some special, provisions to be taken when a teacher teaches their own child. The exam has to be taken by another teacher. That's So you have to know it. The university has to know it. Yeah. Generally, it's not checked, but let's say this is a very law-abiding university, and so it checks that very carefully. And so you could write this down as a conjunctive query. Okay, so here you have the and sign, and you say enrolled SCR. So you're looking for values here. Enrolled SCR. Yeah, a student. Sorry, a student is here. These are students. A student is enrolled in a course C, and with a registration date. And teacher, a professor teaches a course. The same course here as you see, C and C. So we use the same variable to say that this is the same course, and with a certain assignment months or whatever. And then parent PS, P, the professor, the same professor P of here is the parent of the student. Okay, so that's clear. This query will evaluate to true if and only if there is such a situation. And of course, we could also define what the output of a query is. We could define certain variables as output variables, and we could say, well, then the P and S should be the output, parent and student should be the output. But let's forget about output. It's not difficult to handle, but for simplicity, just let's say we want to know whether this query is true or false, and that's it. Okay, as you see, it's exactly the same problem. It's a constraint satisfaction problem. Yeah, it's in its more simplest form. It's exactly the same problem as the crossword puzzle, except that our variables now are explicit variables, and here the variables were these fields. But again, we have to map these variables into these vectors of variables into a relation, into a data relation. And we have to map these horizontals for this field, for instance, for these verticals for this field into a data relation. Okay, and then we have another data relation for this and another one for this, etc. Okay, here we have our data relations and we have vectors of variables. Okay, and we have to map these vectors consistently into these data relations. Consistently means that this S has be equal to this S. You cannot, for one query answer, one variable can only have one value, and exactly one must have exactly one value. Okay. Now we can look actually at the hypergraph associated with this query, and the hypergraph is defined by vertices and edges or hyperedges. The vertices are just the variables here, okay, and the hyperedges are the variables that occur together in one constraint. So this would be a single constraint. This is the constraint satisfaction problem, which has a conjunction of constraints. And to each constraint, you have a constraint relation where you have to map the constraint in, the scope of the constraint, as this is called, in. And then you can look, you can draw this as a hypergraph, okay? And you see immediately that this is a cyclic hypergraph, even though I haven't given you the definition of what cyclic means for hypergraphs. You can see, and I will give you this definition. We'll give you one definition of it. There are so many equivalent definitions, but you can immediately see without any definition that this is cyclic. Now, what happens if I ask, is there any student, is there any student who has a parent such that the student is in one course, but the parent may be in another course, not necessarily in the same course. So that's the same query, except that for course, we here have C and C prime. The courses could be different, okay? So is there any parent this year, yeah, who has a student, and the student has, but not necessarily such that the parent teaches their own student, okay? Their own child. Okay, so if we look at this query, it's very different. It's now suddenly, because of this C doesn't need to coincide with this C, it's suddenly something that you can immediately recognize as an acyclic query. Okay, nobody will question this. This is clearly acyclic. This is an acyclic hypergraph, even though we haven't given the difference. Okay, what is well known, very well known, is that constraint satisfaction problem solving and conjunctive query solving is NP complete. And even though this is the same problem, this was shown in two different communities, in the AI community and in the database community. Different people have shown this result. Actually, it was the same, and that's happening all the time, over and over. And so this is why in this talk I will always speak about queries and CSPs, sometimes about queries, sometimes about CSPs. But you know, it's the same problem, so you will not be angry. You will not mind that sometimes I say query instead of CSP. Okay, I come more from the database world, so query is a little bit more familiar to me, but I also used to work on CSPs. So I will spare you the NP completeness proof. just say you can encode a graph as a binary relation, and then graph coloring. Yeah, you map this binary relation, the edge relation of this graph into a fixed relation, which is red, green, blue, green, red, etc. All the allowed colorings. And if you can find such a homomorphism, then the graph is three-colorable. And here you have all possible pairs of a three-coloring. Now, what is really interesting here is what you can see from this example, even though I will not now explain it in very detail, but it's probably self-explaining too. What is interesting here is that this relation is fixed. Okay, this is a fixed relation. Yeah, so query answering, CSP solving, and actually the homomorphism problem itself, which is again the same problem, is NP hard, even if the target relation is fixed. In this case, it has six. The relation has 6 rows. Okay, but we can even get it with 2 rows NP hard. Okay, so I promised you I would say something more about the definition of acyclic queries, and I will define now what an acyclic query, an acyclic hypergraph or query or CSP is. Okay, so you have here a query or a hypergraph as you want. A query here, a hypergraph here. A query or the associated hypergraph is acyclic if and only if it has a joint tree. That was not the original definition, but it's a very simple one that's very useful. Okay, so what is a joint tree? A joint tree organizes the hyperedges of the hypergraph, or as in this case, the atoms of the query into a tree. So every atom must appear somewhere. So we have 3 atoms here, and the tree has 3, or the forest actually, you should say forest, in this case it's a tree, has 3 different nodes. Yeah, each node is one. You could also just take the hyperedge, but it's one atom. And now we need an additional property, and the property says is a so-called connectedness property. It says those vertices of this tree that contain the same variable form a connected subtree. So let's take a variable p, for instance. P occurs here and p occurs here, and this is in fact connected. P does not occur here. Okay. Now let's. What else can we see? C prime and R are not relevant because they only occur here. Okay, so S, let's say S forms a connected subtree. It is not the case that some variable occurs here and here, but not in the middle. Okay, that would violate this condition. Okay, so if some variable, let's say X, would occur here and would occur here, but not here, then this would not be a connected subtree because it's not connected. Okay, so I think this is it. This means this is the definition by a property that was actually derived later of what an acyclic hypergraph or an acyclic query is. So in case of hypergraphs, you don't write parent, teachers, and enrolled. You have the same definition. Okay. Now, this looks very simple, but actually it's a very, very powerful definition. And I will give you some examples that are more complex than this one, so that you can see that this is actually not really trivial. So let's, for instance, look at this here. This is a hypergraph, and this hypergraph has a joint tree, and here you can see the joint tree. Okay, and this joint tree basically are now only the hyperedges, and the hyperedges are just the sets of vertices that these hyperedges are made of. Okay, so let's see whether, first of all, each of these hyperedge is in fact one node of this tree. Okay, so you can see each hyperedge, HI, for instance, occurs here, the big one occurs here, and then there's ABC that occurs here, etc. And we also have the connectedness condition. Connectedness condition, let's say, for instance, if we have an I here and an I here, there's no other I, and these 2 nodes are connected. Well, here there's not. This is not, again, not a pretty simple example where you can see that everything is connected here. Yeah, A occurs only on these 2, okay, and HI is actually a separator, so you never have any variable that occurs here and here, but not on the entire path. Okay, so this is easy to see. The next one is more complicated to see. So here you have complicated and more complicated. I have added some edges here. So to see that this is not trivially, at least trivially recognizable as acyclic, but it still is an acyclic hypergraph, I have drawn here a cycle. So if you can see there's a cycle BA, AD, DC, and CB. Okay, so if we were looking here at the primal graph of this hypergraph, we would have a cycle in it. And what is even more interesting is that this cycle is not covered by a single edge, okay? By a single hyper edge. It is covered by at least by two hyper edges, by this big one and this big one here, but not, and in addition to this, but if you just look at covering, we have this hyper edge and this, so the cycle goes through both hyper edges, okay? Still, and that's the interesting point, yeah? So that shows the generality of this notion. Still, this hypergraph is acyclic, and here you have now of course we have to change our decomposition here, or our joint tree. We can still have a joint tree, and here you have this ABC hyper edge and ABCDFG hyper edge, and now we have here an A as children A and B, C, and C, D, and A, D. And here, now you can see that it's really not trivial. You have an A here and an A here, and this A appears on the entire path from here to here. Okay, so it forms all the vertices of this joint tree form a decomposition. Okay, form a connected subtree. Sorry, a connected subtree. Okay, so this was it, and now we have again some questions. And one question is, why are acyclic queries so good? That's the first question. And then what's so special about them? Okay, so let me start about the complexity. The acyclic, so as we have already said, in general, query answering or CSP answering is MP complete. And that was shown in AI by Biebel and in the database field by Chandra and Merlin by slightly different proofs, but it's the same problem as we have seen. And what I have already shown here is that they are NP hard even for fixed constraint relations. So NP complete even for fixed constraint relations. In this case, we had a relation with 6, but we can easily show that this also works with only 3, the constraint relation 3, with 3 tuples. Now, in case of acyclic hypergraphs, we have p-time complexity. And this was first noticed by Yannakakis in 81. And we have in 98, Leone Scarcello and myself have determined the precise complexity of this within polynomial time. So it's a subclass of polynomial time. And we have shown that this problem is complete for a very strange class called log-CFL. Log-CFL is a class that is related to context-free languages. It's checking whether a word belongs to a context-free language. And what is really interesting is that this is in NC2. So actually the problem is highly parallelizable, and we have developed parallel algorithms for it. Okay, now let me come to other good properties of acyclic queries. So acyclic queries can be recognized in polynomial time. Yeah, so we can recognize whether a query is acyclic in polynomial time, which is very important. A joint tree for an acyclic query can be built in polynomial time. And again, I say query, but the same is true for constraint satisfaction problem. A Boolean acyclic query can be answered in time, size of the query times maximum size of a relation times log of this. Okay, so this log factor is Turing machine complexity. If we have random access, we don't need that. So the log factor can disappear. And it can be answered in parallel time in NC2 by a specific log-CFL algorithm. Okay? And a non-Boolean query, which we'll not really treat in this talk, but I just want to say this, can be a non-Boolean query could have an exponential number of answers still. Okay? But a non-Boolean query can be answered with polynomial delay. So if there are many answers, it will of course take a long time because you have to enumerate these answers. But if there are few answers, you can compute them one after the other with polynomial delay and also in polynomial time, if there are few answers. So how can we evaluate acyclic queries or acyclic CSPs efficiently? And I said Yannakakis I already referred to Yannakakis, so it's by Yannakakis algorithm. And many of you will know this algorithm, but some may not. And so I want to go very briefly through this algorithm. So here we have a query, and so this is the query again, or the CSP scope, the constraint scopes. And next to each scope or next to each query atom, I have a constraint relation. Okay, so this must match this relation, this must match this relation, this must match this relation, and of course the same y here, the same variables must match the same value. Okay, so how does this work? Basically, we can now assume, because the query is acyclic, that we have a joint tree. So what you see here is actually already a joint tree, and as you see here, we have a Z, here we have a C, and actually, in fact, the vertices we see span a connected subtree. In reality, the forest would be sufficient, but let's, for all relevant cases here, we just can use trees. And so, how can we evaluate this query? Well, we start at the leaves with the evaluation. That's Yannakakis algorithm. And we say, okay, let's take this leaf here, and let's look at the next, at the unique parent of this leaf, and let's look at the common variables. They must coincide, of course. Okay, so there must be, for each variable here, there must be at least one common here. And if there's some tuple without a common variable, we can throw it away. Okay, so the common variable here is the Z. Okay, here the Z is in the second column. Here the Z is in the middle column. Okay, the middle column here has 9 and 4, but there's no 9 and 4 in the second column, so we can throw these tuples away. Okay, so basically, I have represented this with a pair of scissors, because we cut this relation, but in databases, this would be the semi-join operation, okay? We take it, and also in constraints, it's a semi-join operation. Instead of doing the join, we just reduce, it's a semi-join reduction. We reduce this relation here by this relation, okay? By just throwing away every tuple that doesn't match any tuple from this relation, for which there is no single tuple that matches here, okay? And these are clearly useless values. Okay, now we can do the same here. We can also, the remaining relation can still be reduced, namely by this relation. And here you see you have two common variables. And of course, a tuple here can only match with a tuple here if these tuples coincide in both variables. And so we can, again, we can throw away for this tuple here, because this has an 8,4, and there's nothing that starts with 8,4 here, okay? So we can just throw it away, and that's the only tuple we can throw away. It can be seen. I will now not go through the details, but that's how it works. Now we have maximally reduced this relation from below, and now we can continue, and we can reduce this relation with this one, okay? And again, two tuples will fall out, okay? And then we are done. And what the interesting, beautiful thing now is, if there is any tuple left here, and as you can see, there are two, then the problem has a solution. And we can reconstruct the solution from here, because we know this tuple must match with one of these tuples, okay? For instance, with this one, this tuple matches with this one. And this tuple must match with both of these tuples, because we have reduced this relation by both. So there must be a tuple here and a tuple here, so we can easily reconstruct the solution now, actually also in polynomial time, okay? So that's Yannakakis algorithm, and Yannakakis algorithm is not only good for Boolean queries, it's also good for constructing solutions, and iteratively we can construct solutions by this method with polynomial delay. And generally this is done by first also doing the semi-joins or the reductions down, so that we throw away all useless tuples and only then we expand these tuples. Yeah. So basically, if we do the semi-join down, as I have done it here, yeah, and I reduce now everything with from above to below, at the end we will end up with relations where every single tuple occurs in at least one solution. And this is a very nice representation, because there could still be exponentially many solutions, okay? Because I can multiply this in different ways, but it's a polynomial representation where every single tuple must occur in at least one solution. Thus, if I want to ask, is there a solution where Z equals 5? I just have to look here at the Z column, and I can say, no, there is no such solution, because there's no 5 here in those. Okay, good. So I hope that I convinced you that acyclicity is a really nice notion. It's good. We have very efficient algorithms for solving that, for solving acyclic problems. But unfortunately, not all CSPs and not all conjunctive queries are acyclic. But many queries, as has been observed, are nearly acyclic. So the next question I want to attack now is how to generalize query acyclicity. How to generalize query acyclicity. Generalizations come with a notion of width, and width just expresses a degree of cyclicity. Okay, a query can be very, very acyclic, very, how to say, acyclic. Namely, it could be acyclic, and so our generalization should certainly include all acyclic queries. Okay, but it could be a little bit less acyclic. It could be have width 2. Width 2 would be still rather acyclic, but not precisely acyclic. Width 3 is a little bit less, etc. Okay, but generally what we're looking at notions of where there's a constant width cyclicity, let's say. Okay, and so one thing that we ask for in such a good generalization is, one criterion is it should really have that queries of width 1 are the acyclic one, 2 is very likely, very similar to acyclic, but not properly acyclic, 3 is a little bit less, 4 a little bit less, etc. A little bit more cyclic, etc. So it's a measure of cyclicity where 1 should represent acyclicity in the ideal case. What we also want to have is the tractability of recognizability. We want to recognize whether a query has width k, where k is a constant. Okay, so if I want to know whether a query has width 4, it should be recognizable in polynomial time. What we don't want is to compute the exact width in polynomial time, because this will be generally NP hard. Okay. Finally, we want to have tractable query answering. With k queries for fixed k, for a constant k, should be answered efficiently. Or with k, constraint satisfaction problems should be answered efficiently. Okay, and here I show you an example that some of you have probably already seen. I have a large query with, I think, 11 atoms, or a constraint satisfaction problem with 11 constraints. And if you do the hypergraph, it looks very chaotic. And a decomposition method should be an automated method to transform this chaotic hypergraph into something much more structured that has hopefully a small width. And it should look like this. So you see, this is the chaotic hypergraph, and this is what we automatically transform this hypergraph in. Okay, so this is now a decomposition. This decomposition is called a tree decomposition. This is a very, very well-known decomposition. A lot of people, there are thousands and thousands of papers about tree decompositions. Tree decomposition has been defined for hypergraphs. And basically, what does a tree decomposition mean? It means for a hypergraph or for a query, it means the variables that are together in each atom or in each hyperedge here the set of variables should jointly be included in at least one of these bags. So you see you have again a tree, and the tree is made of bags of variables. These are called bags. Every such set that occurs jointly in one constraint or in one hyperedge equivalently, should also be at least a subset of one of the bags, of at least one of the bags. Okay, so let's see, SXX prime CF is a subset of this. Okay, XXX prime SXX prime CF. Okay, is a subset of this, for example. Okay, etc. And again, we have the connectedness condition that we already know from acyclicity. The connectedness condition says that, again, if we take any variable like x prime here, I have already highlighted x prime for this example, all the bags that contain x prime form a connected subtree of the decomposition. Okay, and that's true. This is a connected subtree. It's not that x prime occurs here and only here and nowhere else, and not in between. Okay, so this is again a very simple definition. So what is the width now? The width of this decomposition is 8. The width is always 1, is the largest cardinality of any bag -1 for technical reasons -1, because if you have a single edge, for instance, you would have 2 vertices and the width would be 1 because it's acyclic. So that's the reason. Yeah. Or if you have an acyclic graph, you can do it with so this is this definition for graphs. This comes from the from graphs. Okay. So here you have width 8. 8 is not a very nice width, I have to say, because usually in the solution algorithms this would then appear in the exponent. So we have. What is good about, that's another question, what is good about tree decompositions? Tree decompositions, the optimal tree decompositions, if you have a fixed k, okay? If you look at k equals 4, then you can check whether this hypergraph can be decomposed and whether there is a tree decomposition of width 4 in polynomial time, so efficiently, okay? And queries or CSPs of bounded trees can be evaluated efficiently. So that's the next big advantage, okay? And again, as you see, you have the tree width +1 here in the exponent, or you can even have different bounds. I don't want to go too much detail into it. But now let me say, what is the drawback of tree decompositions? The drawback of tree decompositions is that it doesn't fulfill one of the criteria that we actually postulated that a good decomposition for hypergraphs should have. It is a fantastic decomposition for graphs, but it's not very good for hypergraphs because I'll give you a very simple example. This hypergraph here, okay, that consists only of a single hyperedge x1 to xn, of course, is an acyclic hypergraph, okay, by definition. And its hypergraph decomposition would just contain this atom or this edge here. Yeah, that is a tree, okay, and the tree cannot violate, yeah, the connectedness condition because everything is already in one atom, okay. So this is clearly an acyclic query. So its width should be 1, but unfortunately here the width is 8 because these are here you have this decomposition contains 1 bag, and what we count here is the number of vertices, and the number of vertices are 9 minus 1 is 8. Okay, so if we look at the vertices here, they are 9 minus 1 is 8. So we have a big bag that contains everything, and so we have a very large width. Even though the query is acyclic, because in our joint tree, there would be only one atom, okay? So as a conclusion, I can say that tree decompositions and tree width grammatically fail to capture the essence of query acyclicity. And this is even the case for queries of fixed arity greater than 2, okay? Of classes of queries of fixed arity. And I can also say a similar phenomenon happens if we define tree width not by the width of the primal graph, as I have done here, but if we use the incident graph instead of the originally given hypergraph, and then compute the tree width of this incident graph, very similar phenomenon happen. You cannot capture acyclicity with tree width. Okay, hypergraph acyclicity with tree, hypergraph acyclicity with tree width. Now let's introduce another notion, which we call generalized hypertree width or generalized hypertree decompositions. So again, we have this query, and what we are doing is again we do a tree, but now instead of just having variables in this tree, we have atoms in this tree, just like a joint tree. A joint tree has atoms, but a joint tree has 1 atom per bag, and here we have multiple atoms per bag, and actually we say, let's try what we can do with as few as possible. So here we have 2 atoms per bag, okay? Maximally 2 atoms per bag. So basically what we did is actually, we took this tree decomposition here, and we just tried to cover it by atoms. And we covered basically these variables, and here we were able to cover this set of variables by 2 atoms. Here again, and here again, and we did something else. In order to satisfy the connectedness condition, we had to drop some atoms here. So we put underscores. So basically we took the projection of some atoms. But we can only take the projection of an atom if this atom appears in full somewhere. So here we have the full atom J, and once we have the full atom J, in order to put some intermediate, to squeeze in some, in order to satisfy the connectedness condition, we can put here an XY, and so this XY will be connected here, etc. This X will be connected with this X, because otherwise, if this wasn't there, it would not be connected. But for ensuring the connectedness condition, we can use partial atoms or projection of atoms if we want. If we want, that could be a new relation. It's just a projection of the J relation, okay? Scope of the J relation, okay? So we can use this, we can fix some violation of the connectedness condition that would happen if we didn't have this, because then we would have X here, and X here, but in between we wouldn't have X. We fix it by squeezing in a subset of this atom. Why a subset? Because if we took the full atom, it would again be not connected, because then an unconnectedness would arise from these additional atoms, variables here, okay? So this basically differs in two ways from a joint tree. The first way it differs is that instead of having just one atom, we can have two atoms or two hyperedges or more k hyperedges per bag. And the second one is that once we have used somewhere a full atom, then we can use the atom partially to help achieving the connectedness condition. And now you will see we again have the connectedness condition. So take, for instance, I don't know, Z. Z occurs here and here, and it also occurs here, okay? So X occurs here and here, and it also occurs, it spans basically the bags where X occur span a connected subtree, okay? So here you see the tree decomposition, and here you see the hypertree decomposition. And now we can define what the generalized hypertree width is. This is a generalized hypertree decomposition. What is the generalized hypertree width? It is 2, because we only have at most two atoms that cover. And 2 is much better, okay? Certainly than 8. Unfortunately, now when going to this new decomposition method, what we miss is it is hard to compute. The generalized hypertree width, even for a constant 2, is hard to compute. So checking whether the generalized hypertree width of a query 2 is NP complete. And so this is a problem. It was left open, but in a recent paper, here we showed it for 3, and here we showed it also for 2. And for 1, of course, it's polynomial, because then hypertree with 1 corresponds exactly to acyclic, as you can see, okay? So therefore, we have a little bit modified this notion of hypertree decomposition, and we have added a special condition to it. Of generalized hypertree decomposition, we have added a special condition to it. The special condition means if a variable has disappeared because we have used an atom only partially, okay, then this variable that has disappeared here is not allowed to reappear in the subtree, okay? So that's an additional condition. And with this condition, that variables that have appeared don't reappear in the subtree, we achieve that hypertree decompositions can be for fixed width k can be if we can check if they exist in polynomial time, and we can also compute them in polynomial time. Okay. Now, how to evaluate acyclic queries or CSPs in polynomial time if they have bounded hypertree width? Well, what we will do is we will transform them into equivalent acyclic instances, and then use Yanakakis algorithm. So here we have a query. Here you have a hypertree decomposition of the query, and as you see, we have 2 atoms here instead of 1. But now we are doing the easiest possible thing in the world. We are taking these 2 and we are making a join, and we get a new relation. That's the join of these 2, also G and T, of these 2 relations, G and T. And then we have a single relation. And then suddenly this is simply an acyclic query. Okay, so we transform a cyclic query into an acyclic one by just making joins. And given that we have only a bounded number here, we have, for instance, width 2, we will only be quadratic and not more. If we had width 3, we would be cubic. Okay, and then we transform this into a joint tree, and then we use Yanakakis algorithm, which I showed you for solving the problem. So that's very easy to see that queries of bounded hypertrophies and even of bounded generalized hypertrophies, which are unfortunately difficult to recognize, are solvable in polynomial time. So here are the goodies. What are the real good properties of constraint satisfaction problems or conjunctive queries of bounded hypertrophies. Well, bounded hypertrophies truly generalizes acyclicity. We have seen that it generalizes a joint tree. For fixed k, checking whether the hypertrophy is smaller or equal k is feasible in polynomial time. And actually here we have 2k, the exponent is a little bit annoying, and we hope that in the future we will find better methods. For the moment we don't have much better methods than this. Computing, but k is small, you're looking at 3, 4. Okay, so 2k is still 8, but it's 8 in the size of the query, not in the size of the constraint relations. So we have to think about this too. Computing Hypertree decompositions, if they exist, is feasible with the same bound here. And answering Boolean queries, as we have seen, is also feasible in a very similar, you have an additional exponent k, because you have to do these local joins here, but that's it. So if the k is small, it can be done in polynomial time. If the k is fixed, we can do it in polynomial time. So how do hypertrophies and generalized hypertrophies relate? And here's a nice, I think this is a nice result, because it shows actually that hypertrophies really truly is a 3 approximation of generalized hypertrophies. So the generalized hypertrophies is smaller than the hypertrophies, but the hypertrophies is at most 3 times the generalized hypertrophies. Okay, so what does it mean? Also, it means that classes of queries that have bounded hypertrophies also have bounded generalized hypertrophies, and vice versa. Bounded classes of queries with bounded generalized hypertrophies have bounded hypertrophies. So in practice, at least with respect to boundedness, hypertrophies and generalized hypertrophies don't differ very much, with the big advantage that hypertrophies can be computed in polynomial time for a constant k. Okay, can we go beyond hypertrophies? There have been other notions of width. Most importantly, I would say, so we have acyclicity, tree width, and hypertrophies which generalize both acyclicity and tree width. So hypertrophies is a width that generalizes both acyclicity and tree width, which is, I think, very nice. But there are more general notions, such as fractional hypertrophies and submodular hypertrophies. Unfortunately for this, it was not known whether they can be computed, whether the width, even for constant k, can be computed in polynomial time. For constant, arbitrary constant, this will be, for arbitrary value, sorry, width, this will be NP hard, but that's not what we are after, because we are after small widths, 3, 4, 5, 2, 3, 4, 5. Is this tractable? That was an open problem. Very recently, we solved this, very recently in 2018, and we showed that this is NP complete, even for width 2. For submodular width, it's still open, the best, but they have highly exponential algorithms currently for solving it. So now let me, if I have time, still a little bit, I can define what a fractional, how fractional width works. What is a fractional edge cover? A fractional edge cover is basically you assign a number, a real number, or a rational number between 0 and 1 to each edge, okay? And each node must be covered by at least 1. So here, for instance, you assign 1/2 to each edge, to each hyper edge, and then you take any node, and it has, each of these nodes is in 2 edges, so it's 1/2 plus 1/2, so it's 1. So that's a fractional edge cover. And then the measure rho star of this, so the width, that's the edge cover number, as you call it, rho star, is the sum of all these coverings, of all these numbers. In this case, it's 1.5, okay? And for each query, the interesting thing is an optimal fractional edge cover for Q minimizing rho star of Q. So an edge cover with minimum rho star can be computed in polynomial time via a linear program, okay? So that's very interesting. And then Groh and Marx have shown already in 2006 that the answer to a query of fractional cover of weight rho star of Q is at most the maximum relation and the rho star in the exponent, okay? Now, as we have seen, the rho star can be smaller than the hypertree width, because the hypertree width of such a triangle would be at least 2. You have to put at least 2 edges into one bag. So it would be 2, and here it's 1.5, okay? So now if you look at the triangle query, for instance here, RXY and join SYZ join TXZ, yeah, that states that the triangle query can be solved in n to the 3/2 only. It's very difficult to imagine how can this be? How can this exist? Okay, and I will give you I don't have very much time now left. I don't see also. Anyway, let me see if I can see. Yeah, now I can see Nysret. If his face is already very angry, not yet. Okay. So we have this query. How can we solve this query in n to the 3/2? It's very strange, no? We would at least do the join between two relations, and the join is already quadratic, but still it's possible. And this is an explanation of how it's possible so that you can see what we have to do. We cannot do it, as Grohe and Marx have shown, we cannot do it just by a join program, because every single join between two relations would already be quadratic, okay? So what we could do here is, we could split the relation R, for instance, so the first relation, into two relations, R plus and R minus. The R plus takes all those x values who are heavy x values because they're connected to many y values. What does many mean? Greater than square root of n, where n is the size of this relation, okay? The number of bits or number of values in this relation, okay? And R minus is the contrary, where all the x, you take all the tuples where the x value corresponds to at most square root n, okay? Y values. So once you have that, you can compute the query in the following way. You compute actually two answers and then join them, because this is of course a partition. You partition the relation into R plus and R minus, and you do two different ways of computing it. So now you join this with this, and you observe if you join this with this. What you observe is how many x values can you have, given that every x value must be at more than square root n. You can have only at least square root n, at most square root n x values, because then you have square root n times square root n would already be something that is greater than square root n would be greater than n. So you can have at most square root n x values here. And if you just simply join them with those, you will get n times square root n, okay? That's n 3/2, okay? And now you do the same thing here. You do a similar thing here, not the same thing. That's very important. You can't do the same thing. You do a different thing. Now you take this relation and you join it with the t relation instead. Yeah. Sorry, I forgot to say the t relation now, joining the t relation now is just linear, because you already have x, y, z in this relation, and now you have to just throw away those tuples from the result here that are not contained also in the t relation. That on a random access machine can be done in linear time. So that doesn't cost additional work, because here you already have x, y, z in this relation. You have y and z, x and z, sorry, and x and z is already here. So you just take those tuples of this that contain the x and z that is here, and you can look it up, of course, on a random with random access very fastly, or with indices or whatever. Now here, you have a different situation. You now take the relation t and you join t, and what you have to join is the x. And now you will join each tuple the x value, but there will not be so many joins for each x, because each x here corresponds to fewer than square root of n y's. And again, you will have multiply this only with square root of n. And again, you have n to the 3/3. And then the other one is very simple, because you already have all variables, and you just have to drop out, eliminate those tuples that don't occur here, okay? Or those tuples here that don't occur here in this relation. So that's how it works. Fractional, I think I should stop now, yeah? Fractional hypertree decompositions are just hypertree decompositions where instead of simple joins, you have fractional covers here, okay? That are smaller than k. Yeah, and then everything works again in the same way, and you can compute queries in polynomial time, and this is truly more general than hypertree decompositions. Okay. Now, unfortunately, fractional hypertree decompositions are difficult to are intractable, even for k, even for 2. Checking whether the query has fractional with 2 is intractable, and the same thing is with generalized hypertree decompositions, but we found polynomial cases that are very useful, and I will just show you the first. If a hypergraph has the bounded intersection property, bounded intersection property means that the intersection of each, that there's a fixed constant such that the intersection of the hyper edges are not larger than these constants, okay, for each pair of hyper edges. Yeah, and in this case we can compute everything, fractional and generalized hypertrophies in polynomial time, and then there are many other other properties. I think this is so. What we are studying now, and let me just we show that this is also reasonable. These restrictions are reasonable because in practical cases they occur very much. You can look that up on the slides. And what we are looking now at is we are looking at bounded Babnik-Chervonenkis dimension. Here we could only get an approximation, but we don't have a tractable problem. We are looking also at, we have a first paper at ICHKAI this year on semantic hypertrophies and semantic generalized hypertrophies. What is a semantic hypertrophies or generalized hypertrophies of a query? It's the hypertrophies of its core, basically. Yeah, it's if a query contains if a query is equivalent to a subquery of bounded hypertrophies, then we could use the subquery instead of the query, and we could use all the good things related to the hypertrophies. And we have studied this problem. This is something that initiated with work of Barceló and others, Pablo Barceló. We are looking at algorithms in practice. We are implementing a lot of algorithms in the context of our project, Hypertrack project. And we are looking at the parallelization of two things. Parallelization of decompositions. We have done it for generalized hypertrophies. We have a nice algorithm for parallelization that is we have implemented and tested. That was really published now currently in ICHKAI 2020. And now we are also looking at, we have done some work with students, some very encouraging work already on parallel constraint solving with Hypertree. Thank you very much for your attention. And sorry for taking again a little bit longer, but hopefully there are still a few minutes for questions if you have any.
Yes, thank you very much, Georg, so for your very nice talk. So there are two questions now in chat, which I will read for you. So the first question is from Fuji Tanako. I will summarize it. So he's asking how good the algorithms are in practice, and if there are good algorithms for generating tree decomposition, and if there are also some frameworks for solving problems with the tree decomposition.
Sorry, if they are good? If they are good?
If there are good algorithms for generating the tree decomposition.
Yes.
And
sure.
If there are some frameworks for solving problems based on tree decomposition.
Yes, I think tree decomposition has been much better studied than hypertree decomposition. And there are pretty good algorithms that either compute the tree decomposition precisely for a small k. There is an entire library of such algorithms. I think the first one who has put up a library was Boatlander. Tree decompositions are also sometimes implicitly, I mean, there's many other things. I mean, many algorithms use tree decompositions actually implicitly, so that you don't even have to compute it. Yeah, algorithms based on local consistency, etc. But there are very good algorithms for tree decomposition. The algorithms for hypertree decomposition are less good, but it's not astonishing because it's a stronger concept. But we are now making big progress on this, based on all the research that I have shown you in the last slides. Namely, we have shown properties where we can compute much faster in polynomial time, even generalized hypertree decomposition or fractional hypertree decomposition. And we are now implementing proper hypertree decompositions. We have an algorithm already, we haven't published it yet, on highly parallel machines, multi-core machines, and we are having already good results. And now there is here a difference also between the conjunctive query setting, the database world, and the constraint world. So now I can tell you a little bit the difference between these two worlds. So in the database world, we have long queries, but the queries are, the relations are, the constraint relations are pretty large. So what is really large are the constraint relations, and the queries are usually rather short. They are 10, 12, up to 100 atoms. Yeah. In constraint resolution, in constraint, we have shorter relations. The relations are not so big. They can still be big, but not so big. But we have many constraints, often 100,000 or 10,000 constraints. Yeah. So this is the practical difference. So our methods work very well, and other people have used this already in different systems in the database context. Yeah. So in the database context, there are already several systems. For instance, at Stanford, one system for a graph database, yeah, empty-headed, that uses heavily Hypertree decompositions and uses these Hypertree decompositions and gets many thousands time of speed up, even with query and with parallelization. In the constraint world, we are not yet there completely because these constraints problems are very large and we need better algorithms, and that's what we are working on right now, yeah, and where we also use parallelization. But it's also promising. On the other hand, we can also say conjunctive queries are just one application of constraint satisfaction because it's exactly the same problem, okay? And so for these problems where the queries are not too long, we have very good results, and these results are really pay off because you have to repeat these queries very often just with different data. So it's really useful to decompose the query and then to do simpler algorithms. And that has been validated by other people, not only by us, ourselves. There was another query?
Yes. So
question.
To note to participants, the next session, should have begun in 14:30, but it will begin in 3 minutes, so with 5 minutes delay. So we'll answer two more questions. We'll ask two more questions. So the one is from Tobias Geibinger, who is asking, how does generalized Hypertree width compare with other measures like click width or the incidence or primal graph?
Yes, a click width, generalized Hypertree doesn't generalize click width, but click width in this context is very hard to use. It generalizes all other widths, yeah, incidence width, etc. Okay. And it is, as I have said, it is the most general. Hypertree width is currently the most general computable width that is computable, yeah, for constant k in this context for hypergraphs. Okay. And
yeah, and there is another question from Roland Yap. He's asking, generalization of width become more intractable. So is that the way to go? Well,
it's not. I have to say, okay, can I say something which is, without being impolite, it's not exactly true, because I said it also, but it's not completely true, because there is a width called query width, for instance, yeah, which was introduced by people from Stanford, and it was MP hard to compute, okay? And Hypertree width, which is more general than query width, much more general, yeah, actually is polynomial. So sometimes it actually happens that you get a larger width, yeah, a more general width, let's say, a more general width, which is actually tractable, while the other width is not tractable due to some peculiarity in its definition, yeah. But of course, we have to say, I agree, yeah, that in general, without this example, yeah, the more general a width is, the harder it is to compute. But this is only true for computing the width. It is not necessarily true for solving the problem then on the large relations, okay? So for computing the width, you only need actually to compute, you only need the constraint scopes. You don't need the constraint relations for computing the width, except for some, of course, for some specific widths that also involve the relations, but let's forget about that, yeah? So, yes, it's true, but it may still be worthwhile, especially in the database sector. You have to repeat the same query very often. Every day you have the same query. Every day you ask the database, yeah, is there any anomaly, or is there any violation, like did any student something stupid, etc. Yeah, you can, every single day you have to do this. But not, there are some queries that you do 20 times a day, especially in the news area. So we had a lot of applications with news queries that query keywords of articles in form of conjunctive queries of news articles. Yeah, and here you want to inform people very quickly, so you have to issue these queries hundreds of times a day, more than hundreds of times, thousands of times a day, and then it's really useful to decompose this query. So with constraint satisfaction problems where the scopes don't change very much, but the relations and the values can change, this is really still important to spend some time on the scope, yeah, and then to have a better way of answering the query. But I have to agree, in the database setting, this is still much. This is now people now know that this is good, and we have to work hard to make it also appetizable. How to say, to make it interesting for the constraint satisfaction probability community, CSP community. And I hope that I did a little bit towards this goal in this talk. Thank you very much.
Thank you very much, Georg. So there is another question, but I think we have to close this session. I would like to ask you to stay for 3-5 minutes if some people want to ask still to you questions, and the next session will begin.
Okay.
Thanks a lot for a great talk today and for answering the questions. It was a pleasure to have you here. So
thank you. It was a pleasure to be here. Thank you very much.
And like I said, all the participants who still would like to speak to Georg can stay here. So Roland Yap asked another question. Maybe you can switch, you can unmute your microphone, Roland, and ask directly the question if you want.
Right. So another way of saying the same question is that for the more powerful classes, then usually the meta problem becomes also, unfortunately, much less tractable.
Yes.
Right.
And you say the evaluation problem
and
becomes less
maybe
tractable.
there's inevitable, but I'm just wondering whether, is that the direction to go? Or perhaps another direction is just to find more and more classes which are tractable, but they're not necessarily more powerful.
Yeah.
Just different.
But let me tell you, we have seen hypertrophies, yeah, and the more generalized hypertrophies. Okay, generalized hypertrophies is much more general. Yeah, I mean it can be 3 times better, but the evaluation method is exactly the same. Exactly the same. It's not different. Yeah, it's just that you have to spend more time to discover it, to discover the decomposition. Yeah. Now, if you switch to fractional hypertree, then it's true. We have a more complicated. We have an algorithm that looks at least at first hand more complicated, but actually it's not much more complicated. So again, you have to. Again, if you have generalized, if you have a fractional hypertree decomposition, yeah, it's more general, but the worst case results are not really worse. Yeah, so the evaluation methods are not worse, even though the method is more general. Where we have to spend more time clearly is in discovering a decomposition tree, a fractional, which is a fractional hypertree decomposition, which is more complex than just a hypertree decomposition. Okay, so we may have to spend more time to find the decomposition, but once we have found it, the evaluation is not more complex. Not really. I mean, it's different. It's different, and I don't have time now to explain it. I can explain it also, but I mean, but at least in the worst case, it's not really worse. Yeah. So it's really the effort to find the decomposition, and the effort only depends on the constraint scopes. It doesn't depend on the constraint relations.
Right, but when the constraint relations are very small, then maybe there might be an issue there.
That's possible, but I can't. I mean,
in the database context where the relations can be large,
yeah,
then, that helps you, right?
Yes.
Right,
if the relations
in the combinatorial setting, then the relations are much smaller.
Yeah.
They may not be very small, but they are much smaller than the database setting.
That's true. But I still think even with small relations, this works. Yeah, because even with small relations, we have similar algorithms. Yeah, because due to the fact that if you have to do a lot of joins at the end, yeah, you have to do a lot of, how to say, kind of looking at all these relations and at the end putting them in some way together, either be it now in an explicit way or in an implicit way, in a kind of a join, in kind of a tree, a joint tree or something like that. And so at the end, I don't think that once you have a decomposition, yeah, even if you have small relations. Now, if you have very, very small relations with 2 tuples, maybe one relation with 1 tuple, then you would look at the hybrid method of solving. Then you would take this 1 tuple and so if you have knowledge about the size of the relation, and you do that also in databases actually. Yeah?
No, I mean if you look at tree set, right? The relation is like nothing.
A tree set, yeah. But it's
relation is nothing, right? But you can get a lot of relations though.
Yeah, but interestingly, one has discovered that the smartest algorithms for 3SAT, and there is some work of Jevons with his student, Pete Jevons.
Yeah, I know Peter.
Yeah, and there is some work of this. that actually the smartest 3-sat algorithms, or very smart 3-sat algorithms that are learning and etc., actually implicitly exploit bounded trees, okay, not bounded hypertrophies, yeah, bounded trees. So I think given that hypertrophies is more general, but I think it's also good for 3-sat, yeah. Only that if you have small relations, you can come up easier with some algorithm that actually implicitly already looks at small trees and exploit trees in a certain sense, yeah.
Okay, there is another question from Andreas Salamon.
Hi, Andreas, how are you doing? Long time no see. Jevons and Petke is the paper. Sorry, Jevons and Petke. Yeah.
So, Andreas, do you want to set the question, or should I? You can also directly set it, ask it if you want.
Georg, good to see you. Thank you for your talk. So, in your
I can't hear you. I cannot hear you. Can you speak, please, closer to the microphone, or can you, Nysret, can you read?
Hold on. Is that any better?
Yes.
Yeah.
Okay.
Yes.
Sorry. Hello, Georg, and thank you for your really nice talk. So in your ICHKI paper that you referred to, so you referred to 2 ICHKI papers, but I think there's one which was where you made some progress on the semantic hypertree width, I think it's called. Yeah. So in there, essentially what you did is I mean, the way I see it is there's some really nice argument that these width-based methods are going to work really well as long as the classes of problems that we deal with don't have all different constraints. Because all different constraints end up with these really weird high VC dimensioned kind of setups, and so in some sense you've closed the book really nicely on that on those problems. But since the most common constraint that we use in scheduling and many other kinds of CP is all different, or other kinds of injectivity constraints, do you think there's any hope to use these kind of structural methods there?
Yeah. So you are completely right. The all different constraint is a very, very bad constraint, let's say, but which is very useful.
Yes.
But of course, you don't have it in all queries, yeah. But you don't have it in all situations. But when you have it, what you could certainly do is you could at least reduce the other relations, the remaining relations, or something like that. Yeah, that's what I hope could be done. Yeah. Otherwise, you can future work could combine this. Yeah, I think unfortunately, even the fractional decompositions don't take care of all different constraints, because in order for fractional to be I mean, they could be useful in a certain sense still for all different constraints, but only to a limited extent, let's say. Yeah.
Yeah. All right. Thank you.
But that's probably because GAC and all different is already intractable. So
yeah,
and that's just GAC alone is not even solving the problem.
Exactly. But I mean, usually you have all different constraints with a huge number of other constraints. So maybe you can work from that side and look at first at the other constraint and put them in a nice form, and then put the all different constraints together with it, or something like that. I mean, that's how I imagine it. Yeah. I know that this is a very nasty constraint, let's say. But we looked at a lot of constraints from practice. We have actually a system and a database, a portal, Hypertree, Hyperbench. It's called Hyperbench, where we have benchmarks, etc. And for many constraint satisfaction problems, actually do have low with constraint satisfaction problems that we took from other from benchmarks, etc. Yeah, have low Hypertree width.
Great. Thank you.
Okay, so thank you very much for Georg for answering additional questions. So I think we will close now the sessions. Again, thanks a lot for your talk.
Thank you.
Thank you to all.